So here the add-in is open. We want to use the brown spots, our Poisson distributed response in this Y. We want to use brand and temperature as fixed effects and their interaction. We want to use oven as a random effect. And our distribution is going to be Poisson because we've got count data. That's a natural distributional assumption. And the link function, if I leave this blank, it will just choose the canonical default link function. Or if I know what I want to use, I can choose it here. So the log is in fact the canonical link function for Poisson. So I'm choosing the log here. Doesn't matter if I leave it blank, it's going to do exactly the same thing. So blank or choose log for the Poisson. And then I'm going to run. And you can see it's an iterative process. So it keeps updating until convergence. So we watched it run for a while, and now here's the result from that last iteration when it reached convergence. So just like the least squares output that we see for a regular mixed model, we're getting exactly the same thing because it treated it like it was a regular, normally distributed mixed model. It did that internal transformation. So again, we see things like before we saw the variance components. We see the variance components again here. The scale of these numbers is a bit different because these numbers are on this transformed scale. The transformation is the log. That was our link function. So all of these numbers are on the log scale. They're the log of the count of the number of brown spots. So all of our output is on the log scale because that was our link function. So this intercept, it was 11, it's now 0.11, but that's just by chance. Our brand effect was 2.2, it's now 0.97. The scale of these is totally different. This is the raw, well, this was actually a totally different response also. This was on the scale of the 0 to 20 browning. This is on the scale of the log of the number of brown spots. So we want to keep that in mind that none of these numbers are on the actual original data scale. They're on the log. So we're going to need to back transform in order to talk about these in a paper or in a report or really understand what these mean back on the original data scale. We see again these very highly statistically significant p-values. So it seems like again brand and temperature definitely have an effect, but also the interaction has a statistically significant effect. And so again, we'll focus in on the brand by temperature because that interaction is significant. So here's some fun stuff in JMP. So this output is kind of hard to understand right now because it's on the log scale. These are least squares mean, so not necessarily equivalent to the actual arithmetic mean, but plus we're on the log scale. So logging the data, taking the log of each data point and then taking the average is not the same as taking the average and then taking the log of that number. So we're getting even farther away from the least squares mean being perfectly identifiable with an arithmetic average. So just think of these as a measure of central tendency. This is a really important number, but it's not exactly the average, the arithmetic average. Okay, but cool stuff we can do with JMP here is we can hover our mouse over this title line in this table. So you can see that this is a table. It's even called least squares means table. So this table or this table or this table or even this table with these p-values, anything that looks like a table in the report is something that you can hover your mouse over the title line. You can right click and you can ask for extra stuff that might be hidden. So in the columns, it listed the level, it listed the mean, the least squares mean, it listed the standard error, it gives us the option to choose the lower and upper 95% confidence interval. This is what we want here because we want to be able to transform the confidence limits back to the original scale. So I can select these one by one by right-clicking, choosing the columns, choosing this. Or an easier way, I'll show you that on this table, is I can choose the option button and then right-click, and now it shows me everything at the same time, and so I can choose things multiply and do it faster. So that was just hovering my mouse over the title of a table, the title line of the table, not the title, but the column titles. Hover, right-click, and then choose the extra things in the columns, or hover option right click. So either hover right click or hover option right click. So this table is now the information I want to use to back transform to really understand what this model was telling me. So the next thing I want to do, same thing, hover my mouse over these column titles, right click, and then make into data table. Make into data table. We'll take that table and make it a brand new data table for me in JMP that I can now interact with and, for example, plot these means. So I'm going to use this data table to use in Graph Builder to plot the means and their confidence bands. But I want to do it on the original data scale. So I'm going to take the least squares mean. I'm going to right click on this column. I'm going to say new formula column, transform. And what is the opposite of log? So these were on the log scale. I want to undo that to get them back on the original data scale. So the opposite of log is to exponentiate. So I'm going to do the EXP of that column. So these are now the actual corresponding measures of centrality back on the original data scale. So for the level baking soda 400, this 2.14 is saying that kind of on average, but again, not exactly the arithmetic mean, but a measure of centrality for the baking soda 400 is that a good expected value sort of what I expect to get for the number of brown spots for this level is about 2.14. So I expect just slightly more than 2 brown spots on average, kind of, for this group. For this group, I expect twice as many, over 4 brown spots. For this group, I really don't expect many, almost 0. For this group, I expect a little more than 2.5 brown spots, essentially on average, but again, be really cautious about what you mean by average. It's not exactly the arithmetic mean. Let's check that. Let's go to Analyze, and whoops, I want this data table from our pretzels data table. Let's go to Analyze and Tabulate and look at the arithmetic means for the brown spots. Put the mean in there, put the brand, put the temperature. So here's our arithmetic means, and here's our least squares means. So the baking soda 400, here's our least squares means. The baking soda 400, we've got 2.14. The actual arithmetic mean, 2.16. Really close, not identical, really close. 4.12, 4.16. This one's the most different. There's actually 0. The Lie 400 had no brown spots anywhere for any of the samples. But the estimate of that is slightly higher because we can't actually have it be exactly 0 because the log is not defined there. And so this one actually estimates just slightly higher. So we kind of come close to the bottom of the data scale here. And then the 2.63 here, 2.66 here. So similar, but not identical. So the least squares means are not exactly the arithmetic means, even here where we've got full data. Okay, so we wanted those exp of the least squares means, but we also want to do that for the lower and upper confidence limits. We wanted to save these confidence limits because you can't actually do this for the standard error. So it's maybe tempting to exponentiate the least squares means and exponentiate the standard error and then build your own confidence intervals where you take this plus or minus 1.96 of this or 2 times this or whatever multiplier you're using. But don't do that. That is not true. That will not be accurate. The standard errors do not back transform the same way because we were squaring things to get a standard error. This is not going to be directly translatable back. If you wanted to take the standard error back onto the original data scale, you have to use something called the delta method. You can read about this in that SAS for Mixed Models book if you'd like to, or Google this. But much easier is we ignore the standard error and we just back transform the endpoints of the confidence interval that was created on the log scale. When we back transform the endpoints, that works. So we can back transform individual points. We just can't back transform a variance or a standard error. So we're going to back transform the lower 95% confidence interval by right-clicking, new formula column, transform, and exp. We'll do the same thing for the upper 95%. new formula column, transform exp. And then we can go to graph and graph builder and we can explore these. So let's pull the exp of the least squares means into y, and let's move them around by the level. And now we can do a cool thing where we use this interval spot here and we put our own special interval. So we have the exp of the lower and upper limits, pull both of those into the interval, and it gives us our own special interval. So this is really cool that you can actually specify your own user entered intervals here. So here we have the corresponding essentially least squares means, but back on the original data scale. So this is the number of brown spots. So let's say these are the back transformed number of brown spots. And actually I'm going to say back transformed LSMeans for number of brown spots versus the level. Okay, so we've got a reasonable plot here, but there's a few other things we might want to do. One of them is, instead of having these levels, I might actually want my two variables again, my baking soda versus lye and my 400 versus 450, so the brand and the temperature. So let's go back to this little data table. And here's a trick we can use to pull out the brand and temperature really quickly. We can right-click on this new formula column, and we can use this character and first word and last word. So first word, I'll do first, and then I'll do new formula column character last word. And it didn't quite pull out what I think the first and last words are. What it did is where it saw a space, that's where it separated it. So it took baking as the first word, and it took soda 400 as the last word. It took lye 400 as the first word and also as the last word, because it just thinks there's one word. So it didn't quite do what I wanted, but I can fix this. The problem is it thought that the space was the delimiter, and I wanted it to think the comma was the delimiter. So if I double click on this, I see the formula that it created when it did that formula. I'll edit the formula. And if I hover over this, I should get some extra information about what this does. Or if I select this over here from the character word and hover here, it'll tell me a little bit more about it. Basically, what I need to do here is click in here and add an extra argument. So it's word, it's the last word, and then comma, and then the next argument is it's the variable called level, and then I want to add a comma, so I add a new argument, and my new argument is just to put the delimiter, the comma, into quotation marks. So quotation mark, comma, quotation mark. So I've added a new argument to this function. So it's asking for the last word from the column called level, where the delimiter is a comma. I'll say okay, and that worked. Let me also change the name of this to temperature. And then let's fix this one also. So let's call this one brand. And let's edit the formula by clicking in there, comma, quotation marks, comma, quotation marks. So we added the delimiter of comma. Say okay, and now we've got the brands correctly. So that's a really cool thing that you can, for the least squares means, right-click new formula column and find all these things that are relevant to continuous data. For something categorical or words, you get different options here, but there's some really cool stuff here to help you with manipulating your data. So now let's go back to that graph builder. And now we've got the temp and brand here. So I could pull level back out, and I could put temp down here, and I could nest it within brand or the other way around. So here I've got the two temps nested within the brand. If I wanted instead to make this an interaction plot, I could take the brand back off and put it in the overlay, and then I could connect these guys with lines. So if I do, that got weird with the, yeah, let's take the point off. That looks much better. So now we've got the brand as the overlay and the temperature as the x-axis thing, and then the back transformed LSMeans as the response. So this makes our interaction plot. If I don't like the way this looks, I can right click in the middle, go to customize. And for example, on those error bars, I might want them fatter. So let's make the line width thicker. And the end cap, I don't like how wide they are, so let's make them maybe tiny. So I think that looks better. So let's do the same thing for the other error bar. Make it thicker, make the end cap tiny. And I like that better. Next thing I could do, double click on this axis and do stuff with the axis. Let's add some minor ticks in between so you can watch what happens over here. I added these little minor ticks in between. Let's add grid marks at the major ticks and also at the minor ticks. So I'm going to get this pretty grid background. Let's add a reference value. Let's say that we think 2.5 is a comparison level. 2.5 brown spots is something that we want to mark on this plot. I'll make it red. I'll make it thicker. I'll call that reference. And I'll add that line. And so it's going to label it reference and put this line there. And then let's add a range where we go down to 2.25 and up to 2.75. So I'm just a quarter above and below that reference. Let's make it red. I won't label this. I'll just add that. I'll say OK. And so now I can see the reference line with the reference range that helps me sort of look across the plot and see that this is not different than that. This is not different, but this one is, and this one is different than that reference line. So if this is the plot I like, I can click done. If I want to change things with the legend, right-clicking here is an option, or I could not show the legend at all. I'll go back to showing the legend, or even legend position. I could put it inside on the right side of that plot and maybe stretch the plot out more so I can see it better. So lots of stuff I can do here. If I want to save this into my paper, and again, you can always click in things. You can click over here and edit. I could call this a different variable name if I want to, but when I'm happy with the plot, I can save it in so many ways. I can save this plot by going to File, and if you're on Windows, it's File Save As. If you're on Mac, it's File Export. So I could go to File Export on Mac and save it as a specific image file type, or I could drop it straight into a PowerPoint slide. So I'll click the open file after saving, and then it'll just open. So that's dropped it into a PowerPoint slide. Or if I have a data table and I want to save this out, I could also save this by File Export. If I click on the data table, I see different options, no longer the image. Now I could save it as an Excel sheet, for example. So lots of things I can do to save out what I'm working on. If I want to save out this report, File Save As or File Export, and I can save it again in a million different ways. But if I dropped it into PowerPoint, it would take each element and drop it on a different slide for me. So lots of ways to save this out and use this in my manuscript that I'm writing. There's one more topic that I think is very important to mention, and that is over dispersion. In the slides, I had mentioned that the integral approximation methods actually give you a test for the over dispersion. You can also get tests of over dispersion if you're using these models without the mixed component, if you're using them just in JMP with the generalized linear models. But using this linearization method of restricted pseudo likelihood, we don't get the interval approximation method or the test of over dispersion. We still actually need to worry about it sometimes. So if you know anything about fitting distributions, let's look at distribution here for example, let's use this and this and this, our normal, Poisson, and binomial. And let's stack these guys. So here was our approximately normally distributed after fitting the model. Here's our approximately Poisson after fitting the model, and our approximately binomial after fitting the model. So again, just because they don't look perfect before is okay. You really want to look at the residuals for the normal. And in these two cases, you're really looking at the conditional distributions. So this is okay. These are reasonable for the ways that we've modeled them. But one thing we might want to worry about is this normal distribution. If I fit a normal distribution to this guy. Let's see. When it estimates the normal distribution, so here it fit an approximate normal, it shows me that it fits a location, a mean, and a dispersion variance. So it estimates a mean and it estimates a variance. If I take the next one, try to fit a Poisson, it's a discrete fit. There's the Poisson. When I fit the Poisson distribution, that's a continuous count. So it's with these integer values. So that's why you see these little steps, is because it gives a probability for that whole integer, for this one. So it's, you can see it's sort of long-tailed. It's chunky here at the bottom and then a long tail. When we fit the Poisson, we only get this one parameter. So the normal gave us the mean and the variance. For the Poisson, we only get the mean. By definition, in the Poisson distribution, the mean and the variance are forced to be the same. So because we don't get to estimate the variance separately, that's why we might have this over-dispersion problem for the Poisson. So if we want to figure out if we had over-dispersion, one way to do that is to fit this with one of the quadrature or the Laplace method, but that's not an option with our add-in. Another thing we can try is to, with the Poisson distribution, we can fit, so these generalized linear mixed models don't have a residual the same way that our normal assumption models have a residual. So even though we're seeing the output as though there is a residual variance, this is just a different type of model. So let's go back to the add-in and back to that, our second model, brown spots as a Poisson. Either leave it blank or use the log as the link function. Oven is our random effect, our fixed effects, our brand, temp, and the interaction. And now here's what we can do to deal with figuring out if we have over-dispersion or a problem with over-dispersion. We can add as a random effect essentially something that has the residual. There are several ways we could do this. We basically want to put a term in that has a different value for each row in the data set. So one thing we could do is create a new column, and we could initialize this data with sequence data from 1 to 24 and call this row. And so now we have a different value for each row. So we could now use the row as a random effect here. Another way to define that is if we know which oven it is, we know which brand it is, and we know which temperature it is, the interaction of those three things also equally defines. So I can either use the interaction term of all three things, because that will give a different value for each of these, or I can use, let's remove that, I can use this new row effect, but I need the row to be nominal instead. I don't know why I hit the cross button, but thankfully it just added it. Okay, so I can put the row in here, or I can put the oven by brand by temperature interaction. It needs to be random because we're treating this as a variance, because we're trying to figure out if we had extra variance that wasn't accounted for by our Poisson, which forces the variance to be equal to the mean. So this is giving us an extra variance term to test. So now when we run this model, we can see that it does, in fact, it takes essentially all of the residual variance, so there's nothing left here, and kind of puts it into the row. And we can see that, yeah, there was a chunk of variance that we needed to deal with, and so perhaps that makes a difference. Let's look at the effect details here, and specifically at these standard errors. So let's let me rerun this the way we did before. So brown spots, Poisson distribution, the link is the log. It doesn't matter if I put it there or not. The brand and temperature, and brand by temperature, the random effect was oven. So this is the model we ran before without that row effect. So when we ran the model before, so the standard errors in our old model were 0.12 for the intercept, 0.10 for brand, temperature, and the interaction. You can see we've dropped them considerably. They're less than half the size after we account for that individual experimental unit variance. So in fact, it does actually, it's going to make us have tighter confidence intervals. So let's look at the confidence intervals for our brand by temperature. Again, option, right click, choose lower and upper. And over here under effect details, brand by temp, option right click, lower and upper. You can see that we've got much wider confidence intervals here than we do here because those standard errors are smaller here than they are here. So one last thing that we haven't really talked about is I've been really focusing on the least squares means and their lower and upper confidence and back transforming that to the original data scale. I want to warn you to be really cautious if you're going to try to do comparisons of differences, because remember, when you back transform, you've got to back transform that whole function. So if you've got the difference of two logged things, like if we did for brand, if we did the t-test for the two brands averaged over the temperatures, this difference that's calculated, this 1.89, this difference of two logged groups, the difference of the log of some things minus the log of some things, if we exponentiate that, that actually turns into a ratio. So when we back transform this kind of information, and to back transform it, by the way, we would want to put the ordered differences report, because now we get a table. So then we can right click and we can say make into data table, and we can back transform this difference, lower and upper confidence limits. But this now needs to be interpreted as a ratio instead of a difference, because back transforming a difference from the log scale is exponentiating a difference from the log scale, which is going to be a ratio. So just super caution for any interpretation of any differences. Be very careful about contrasts or pairwise differences or anything like that. Make sure you really understand what that's going to mean back on the original data scale. So the final thing I want to mention is where you can get more information. And that is, again, you can go to that add-in download page, download the add-in, and also find 7 more examples and a couple more videos covering those examples. And also you can post your questions at the bottom of that and ask Meichen Dong, the author of this add-in, any questions that you have, or you're welcome to send questions to our email address for the academic team at academic@jump.com.